In this section, I will show the basic ideas of the Bayesian approach, which is of course a topic of interest in this course. First, let's move back to the example of the surgeries and testing the success of these new surgeries. Assume that the first surgeon experienced in the past another technique with similar difficulties, and he remembers that the first 20 operations were the most difficult. So, to make a final judgment on the new technique, he will likely combine this historical information with the outcome of the current experiment. In other words, he will adjust the obtained proportion, the success rate 9 out of 12, in view of the past experiments. This is a process that can be performed in a Bayesian analysis. Let's think about another example. When planning a phase 3 study, comparing a new treatment with an old treatment for breast cancer. Background information is always incorporated in the protocol because typically a lot of background information is available. When it comes to analyzing the data, this background information is not any longer incorporated in the statistical analysis. For example, when a small-scale clinical trial leads to an unexpected positive result, for instance, a p-value smaller than 0.01 in favor of the new treatment, the company will be very happy. If, however, in the past, none of such similar drugs had resulted in a large effect, then we would probably be much more cautious after looking at these results. Take another example. A new mouthwash is introduced into the market, and a study is set up to show its effects. The study must evaluate whether the daily use of a new mouthwash before toothbrushing reduces the plaque. The result was that the new mouthwash reduced plaque 25%, with a 95% confidence interval of 10 up to 40%. This is very nice, but in a previous trial, the overall reduction in plaque lied in between 5 and 15%. And experts argue that the plaque reduction will probably not exceed 30%. So, what can we then conclude? From these examples, it's clear that very often we want to combine information from past experiments or prior knowledge with a current experiment. And this is accomplished in a Bayesian approach. Fundamental in this Bayesian analysis is the Bayes theorem. Or the central idea of the Bayesian approach is that we combine the data, which we call the likelihood, with your prior knowledge, which we call the prior probability, to update the information on the parameter in order to result in a revised probability associated with the parameter, which we will call the posterior probability. So, data together with prior knowledge leads to posterior probability. The reason that we write here your prior knowledge is to indicate that this prior knowledge can be subjective. What I think or what my prior knowledge is could be different from your prior knowledge. In this way, the Bayesian framework could lead to a subjective results. This also implies that probability statements not necessarily have a long-run frequency interpretation as in the frequentist approach. To illustrate further the idea of Bayesian analysis, we will illustrate the Bayesian way of thinking in daily life. As a first example, suppose that you come to visit Belgium for the first time. Possibly you have already looked into a travel guide or you have spoken already with some Belgians, and based on that you have your prior view on the Belgians. Then you come to Belgium, you arrive in Belgium, and you meet some Belgians. This is your data. Once you return, you will have a revised impression of how Belgian people are. This is your posterior. The longer you have stayed in Belgium, the more data you collected, because the more people you have seen and the stronger your data. But was your visit only for a very short time, then possibly your prior is more important than your data. Let's look at a second example. Suppose that a company wishes to launch for a first time an energy drink. The market director has a lot of experience in this and he believes that the drink will be successful. That's his prior knowledge, his prior belief. To strengthen his belief, he conducts a small-scale experiment. That's the data. After this experiment, his prior will have changed. He will have updated this, and maybe his faith will have strengthened or weakened. Suppose patients treated for cerebral vascular accidents with thrombolytic agents suffer from severe bleeding accidents. In a previous trial, 20% of the patients suffered from these bleedings. However, suppose that also a small pilot trial was conducted, which resulted in 10% of the patients. So what can we now conclude for the true prevalence of severe bleeding accidents? So we have our prior in the historical studies, we have collected data in a pilot study, and we can combine this prior with the data to obtain a new idea about this. This is the posterior. So Bayes' theorem will help us to combine this prior with the data in order to obtain a posterior. The simplest case of Bayes' theorem occurs when there are only two possible events, say an event A and an event B. For example, A represents the disease status of a patient, diseased, and we denote a patient which is not diseased by AC. B indicates the result of a diagnostic test. B is a positive diagnostic test and BC corresponds to a negative diagnostic test. Bayes' theorem then describes the relationship between the probability that A occurs and the probability that B occurs. And it's based on the property that the probability of A and B together can be written as a product of the marginal probability of observing A multiplied with the probability of observing B if we know A, so the conditional probability of B given A. In a similar way, this joint probability for A and B can be written as the marginal probability of observing B times the conditional probability of A conditional on B. This split up leads to the basic form of Bayes' theorem, given by the probability of B conditional on A is equal to the part here on the right hand side, that's the probability of A conditional on B times the probability of B divided by this component, the probability of A. So this Bayes' theorem relates the probability of B given A with the probability of A given B. And that's why this theorem is also called the theorem on the inverse probability. Now, because of the law of total probability, we can further rewrite here this expression, the probability of A. Indeed, the probability of A is equal to the conditional probability of A conditional on B times the probability of B plus the conditional probability of A conditional on BC times the probability for BC. So this is the second version of Bayes' theorem. Similar expressions can be derived, of course, by reversing the roles of A and B in the two formulations of Bayes' theorem. So let's look at an example and show how Bayes' theorem can be used. This example deals with the positive and negative predictive value and how it can be derived from the sensitivity and the specificity of an experiment. So the sensitivity of an experiment is defined as a probability of a positive diagnostic test given the patient is diseased. The specificity is a probability of a negative diagnostic test if the patient is not diseased. The positive predictive value, which is mainly of interest, is the probability of being diseased if the test was positive. The negative predictive value is the probability that you're not diseased if the test was negative. Finally, the prevalence is equal to the probability to be diseased. So Bayes' theorem expresses the positive and negative predictive value as a function of the sensitivity, the specificity, and the marginal probability, namely the prevalence. We will show how this works in an experiment. So here we see the results of a Folin-Wu blood test, which is a screening test for diabetes. So this table summarizes the results of the test with respect to the diabetic status of the patients. So from this table, it's easy to obtain the sensitivity as the number of truly diabetic patients with a positive test result divided by the total number of diabetic patients. The specificity of the test is the number of non-diabetic patients for which the test was negative divided by the number of non-diabetic patients in the study. So here we find a sensitivity of 0.8 and a specificity of 0.9. The prevalence in this study is the number of diabetic patients divided by the total number of patients in this study, so 70 over 580, which is equal to 0.12. So we can use Bayes' theorem on this experiment to obtain the positive predictive value. Let D plus denote that patient suffers from diabetics, T plus denote a positive screening test, and similarly D minus and T minus correspond to the negative results. So here, this is Bayes' theorem, which relates the conditional probability of this diabetic status conditional on the test result with the probability of the test result conditional on the disease status. We can rewrite this expression of Bayes' theorem in terms of sensitivity, specificity, and prevalence, since, of course, this component, the conditional probability of a positive test result conditional on the disease status, this is a sensitivity. The probability for disease status being positive, so being diabetic, that's the prevalence. Here in the denominator, we have exactly the same outcomes here, so that's the sensitivity times the prevalence, plus the probability of a positive test result conditional on being non-diabetic, that is equal to 1 minus the probability of a negative test result given the patient is non-diabetic. And that is, of course, equal to 1 minus the specificity. The probability for being non-diabetic is then of course also equal to 1 minus the probability of being diabetic and thus equal to 1 minus the prevalence. So here we see that the positive predictive value is written in terms of the sensitivity, the specificity, and the prevalence. The predictive value for a certain population is therefore obtained by plugging in the prevalence values for that population in this expression. For instance, if we know that the prevalence is equal to 0.03, which is the world prevalence of diabetics, then we find as the positive predictive value of 20% and negative predictive value of 99%. Of course, for another population, if we would change it, this would also change the positive and negative predictive value. But it's easy to obtain it by plugging it into the Bayes theorem. Assume now that a physician wonders whether a patient suffers from diabetics. In the population, the general prevalence is, for instance, 0.10. Suppose now that the following blood test shows a positive result for that patient. Then we can combine this test result with the prior prevalence in the population to obtain a posterior probability for being diabetic equal to 0.47. So this outcome combines the prior knowledge of diabetics with the data, the test result in this case. Suppose now, however, that this 10% is not coming from a certain experiment, but it's just the prior probability that the physician has. Then, of course, these probabilities do not have any longer the long-run frequency interpretation as in the frequentist setting. So, in the next chapters, we will discuss Bayes' theorem further, such that it becomes more useful in statistical practice. We will look back at examples such as those seen in the previous chapter, and we'll always compare the Bayesian analysis with the classical frequentist analysis. It will take some time to understand what we can do and to be able to use it in practice, but I think it's worth the effort. As an example of a Bayesian analysis, we will reanalyze the toenail data using Winbugs, which is a very popular Bayesian software tool. And in the next slide, I will show some results of the Bayesian analysis. Plot A shows our posterior probability about the difference between the two treatments, so about delta. What we can see is that the posterior probability that delta, the difference, is positive is very large. Indeed, the area under the curve for the delta values larger than 0 is 98%. On the right-hand side, we look at our posterior belief for the ratio mu1 over mu2. Again, we see that this ratio is much larger than 1. In the third example, we reanalyze our data, but we include some prior information being rather skeptical about these new treatments or about this treatment difference. In this setting, we see that this prior has indeed changed as compared to the previous experiments. And finally, this is again the ratio, but where we have included information about the variance. So clearly, this result again changes our posterior belief about this ratio. So why should we continue with a Bayesian approach? There are several practical reasons that drive the recent popularity of Bayesian analysis, next to the philosophical difference with, for instance, a frequentist analysis. And one of them is that it's very simple think about problems and answering questions. It is like how we think about problems in daily life. It allows also a lot of flexibility in making inference on a wide range of models. Think about data augmentation, hierarchical models, etc. The possibility of incorporating of prior information can also be an advantage. The development of efficient inference and sampling tools is also useful. Very often, this Bayesian analysis is much easier as a frequentist analysis. And now, especially with the development of very fast computers and fast algorithms, this is an advantage. I have mentioned already that the fundamental theorem in Bayesian analysis is coming from Bayes' theorem, developed by Thomas Bayes. Thomas Bayes was born in 1701 and died in 1761. He was a minister and had a lot of interest in mathematics. None of his work was published during his life, but published after his death. Laplace then reinvented the Bayes theorem because he was not aware of Bayes' work. Now, the Bayesian computational procedures have changed a lot. Before the 1980s, analysis was always conducted in a conjugate analysis in which analytical calculations are possible. We, in this course, will also start with this conjugate analysis. In the early 80s, numerical integration and Monte Carlo integrations were developed, later on the Laplace approximations, and in the late 80s, the Gibbs sampler. The development of the Gibbs sampler, and especially the development of software called bugs, has resulted in a growth of the use of Bayesian methods. So Bayesian statistics has not been widely accepted for a long time, but nowadays more and more people are using Bayesian methodology. Each viewpoint, of course, has its advantages, and I think you should use the Bayesian method whenever it is appropriate. In the medical world, it has taken much longer to accept the Bayesian methodology as compared to the general statistical community, but also nowadays in the medical world, Bayesian methods are more and more being accepted. Different statistical software can be used for Bayesian analysis. I would like to mention the software package R with, for instance, packages INLA and JAX as important software tools. Next to that, I would like to mention the software bugs or WinBugs, on which I will focus also in this course. And then as a third software tool, SAS, with procedures ProcGenMod, ProcLiveRec, ProcMCMC that allow a Bayesian analysis.